Okay, to start with, we'll work with the closed bosonic string. Though very soon we'll move also to the open bosonic string, discuss the superstring at the same time. So but today's lecture is just about closed bosonic string. Okay, so let us remember the basic formalism. Because we're on the sphere, 3 of the vertex operators have to be fixed. The 4th one, or the 5th, the remaining ones integrated. Okay, so we're going to now today talk about the simplest case, namely that of 3-particle scattering.
Yeah, I just have a question
yes.
related to a recent paper that appeared 2 weeks ago.
Yes.
About the string propagator. So, common knowledge is that unless obviously, as you said, we have to fix 3 point and keep the integrate the other point for. There was a paper by Massless and company 2 weeks back in which they showed that it was the 2-point the string-to-string scattering amplitude was assumed to be 0 earlier because of the SL2R volume that appears in the denominator. However, I think they have shown that there's another infinity that appears in the numerator and which gives some finite contribution.
Yeah.
So I was just wondering whether
I looked at the paper.
Yeah, we could talk about that paper.
We could. I didn't completely understand it, actually, I have to say. The thing about it that I didn't understand is the following. I didn't understand what they wanted, what they thought the correct answer should be. Suppose we're doing field theory. Let's go back to that. Let's go back to this question. They probably have some one cut, one not. But let's go back to this question. The question, suppose we're doing field theory. Okay, we've got a scalar field. We want to compute its 2-point function. Okay, so we've got phi of p, phi of minus p. We know what this is with appropriate normalization. It's, let's say, minus p prime, delta of d p minus p prime over p squared plus m squared. Now, if we calculate this on shell, namely at p squared plus m squared equals 0, the answer to the propagator is equal to infinity. So in field theory, propagators are meaningful because we can go off shell. However, if you go on shell, there's nothing to compute, you get infinity. Now there's something else you might want to compute, which is, this propagator is this line, but you may want to add external lines to it, which is adding 2 propagators to it. You may want to, in Feynman diagrams, we often compute truncated Feynman diagrams. With every external line, you add a factor of p squared plus m squared in the numerator.
Yes. Yeah.
And actually, as we will see, this is what string theory calculates it with higher point functions. Okay, so you might think, okay, well, what we should be doing here is truncating both insertions. In which case, we will get delta times p squared plus m squared, which also is not very interesting on shell because it's 0. So what did they want to get? I couldn't understand. I couldn't understand at that level. What is the answer they wanted? They go through some song and dance about what they get, which may or may not be correct, but I couldn't understand what they were after to start with. Now, presumably what they were after was the residue of this pole, because that is meaningful in physics. It gives you the strength with which a particular operator creates a particle. Okay? Presumably they were after that, but what natural observer computes the residue? I couldn't understand it. Okay, that's largely probably my lack of understanding.
I'm sorry, this is probably tangential, but I think this is...
Yeah, but in the end, you see, at most what you can get is a residue, because that's the only information.
Yeah, I think they say that they reproduce the free particle propagator.
Well, I mean, the particles are on shell. P squared is equal to m squared. What else could it be? I basically couldn't understand it. Okay, I mean, no doubt there is deep thinking behind it, but I couldn't understand it. So let's, okay.
Sorry.
Not at all, not at all. No, I mean, actually, Lata also came and asked me whether I could lecture about that. So I looked at it. I looked at it just for a couple of minutes, but what I couldn't understand what question they wanted to answer. There's a second question about how they answer it. But I could get that. So, okay, it's my limitation, but till we get that straight, we'll ignore that. Okay, fine. Okay, so we've got so as we've just said, in a quantum field theory, on-shell questions associated with two-point functions don't have a very clear answer. Okay, actually, there is one piece of information, which is presumably what these guys were after, though I couldn't understand what they did answer that question, which is what is the residue of the pole? That is interesting, and we are not going to be able to directly get it. We will deduce it from unitarity in our way of doing it, and presumably that is the element that they were able to do without appealing to unitarity directly. Okay, but anyway, it's a subtle issue. Let's put it aside. Okay, great. So we're going to start just with 3-point scattering. Okay, now, right. Now, 3-point scattering is non-trivial both from the point of view of string theory and field theory. 3-point scattering is an interesting observable. Before we start actually computing 3-point scattering, there are 2 or 3 things to say about it in general. Firstly, what can 3-point scattering functions depend on? Okay, suppose we've got 3 particles. To start with, let's make them 3 scalars. And their momenta are P1, P2, and P3. Okay, now a 3-particle S matrix has to be Lorentz invariant. So it can depend on dot products of P's. Now, P1 squared by the on-shell condition is minus M1 squared. So that's not scattering data, it's just some number. So you might think, well, it can depend on P1 dot P2 and the 2 related guys, P1 dot P3 and P2 dot P3. However, a moment's thought will tell you that this is also not data, because this is equal to half of P1 plus P2 the whole thing squared minus P1 squared minus P2 squared.
And that's just P3 squared.
But by momentum conservation, exactly, this is P3 squared minus P1 squared minus P2 squared, each of which can be substituted for their masses. M3 squared minus M1 squared minus M2 squared. So you see something interesting. 3-point scattering data for 3 scalars in quantum field theory is not a function of anything. It's a number. Okay? So what we're after when we're trying to compute 3-point scattering is just some number that you can get different numbers when you change the particles. Now, as we will see as we go along, this was true for scalar particles. When you're scattering vectors, for instance, in addition to the momentum, you have to specify the polarization. Same is true for gravitons. Okay? And now the amount of data is not so simple. In fact, classifying the data is a little bit of work. However, you see that it's a finite amount, because what you have, let's say you have epsilon 1, epsilon 2, epsilon 3. You would have to find all ways of forming Lorentz invariants involving contractions of epsilons with epsilons, epsilons with p's, and p's with p's. P's with p's we've seen there's nothing, so it's all epsilon with p's and epsilons with epsilons. Now you will have to find all ways of doing this. This is truly independent data, but you have to make sure that it's gauge invariant. What does that mean? Firstly, all our epsilons will be such that epsilon dot k.
So you are considering a massless.
Yeah, so say we're looking at photons.
Photons or graviton.
Yeah, photons are very equivalent statements for gravitons. So epsilon I dot ki will have to be equal to 0. This is the Lorentz gauge condition, if you like. We want to work in some gauge. We want to preserve Lorentz invariance, so there's basically no real option. Okay? However, this is not the end of the matter. You see, working in Lorentz gauge doesn't completely fix gauge. What doesn't it do? It doesn't fix gauge. See, suppose you fix the gauge del mu a mu is equal to 0. A mu goes to a mu plus d mu chi, this is a gauge transformation, is unfixed provided del mu of the new thing is also 0. So the ambiguity is for functions chi such that del square chi is equal to 0. Now, this sounds like very specific ambiguity. It's only ambiguity by harmonic functions. And in general, if you're working off shell, it's true. The length gauge almost fixes gauge. But we're talking about how gauge is fixed for on-shell scattering particles. And all the on-shell scattering particles obey k square equals 0. So this tells us that modulo the fact that k square, this is just k square equals 0. Modulo the fact that k square equals 0, but that's true of on-shell particles. Okay? It tells us that epsilon mu goes to epsilon mu plus k mu of chi of k for any k that obeys k square equals 0. But all the k's we deal with obey k square equals 0 is an allowed gauge transformation. Okay? So all our scattering amplitudes have to have this invariance. They have to be functions that are invariant under epsilon goes to epsilon plus k. Because this chi was a function of k, what that means is that you could separately shift epsilon k1, k2 and k3 because you're shifting them with separate numbers. So it has to have shift invariance of epsilon 1 goes to epsilon 1 plus k1 and separately shift invariance of epsilon 2 goes to epsilon 2 plus k2 and separately epsilon 3 goes to epsilon 3 plus k3. Okay? Also for 3 photons.
Chi can be different for different.
Yeah, chi is a function of k, so it takes a different value at k1, different value at k2, different value at k3. So in particular, it could be 1 at k1, 0 at k2 and k3, or 1 and k2, 0 at k3. It could be anything, right? Okay? Therefore, what you need is some functions. So what is an S matrix for photons? An S matrix for photons is a map from 3 momenta, all of which are on shell, and 3 polarizations, all of which are orthogonal to their momenta, to numbers epsilon k, epsilon k, epsilon k, such that the resultant combination is invariant under every shift. Epsilon I goes to epsilon I plus ki.
I think this chi is only one scalar function or 3 scalar functions?
It's one scalar function, but it's a function of k.
I am saying that at the same time, for epsilon 1, so these are I indices, right?
Yes.
But this every I, there can be different chi I or
No.
just chi is
At
against field.
chi at any vector k is some number.
Okay.
So let's choose, for simplicity, let's choose chi so that it's peaked around k1 and 0 at k2 and k3. This tells us that our S matrix has to be invariant under epsilon 1 goes to epsilon 1 plus k1. Separately, the same argument tells us also has to be invariant under epsilon 1 2. That's the only thing that's the end result. Okay, so let me say it we'll say it again. An S matrix for 3 photons is a map from 3 k's and 3 epsilons. Each of the epsilons is transverse with respect to its own k. Epsilon I dot ki is 0. The map is linear in the epsilons. Why? Because epsilon is polarization data. You have one polarization per scattering particle. It makes no sense for it to be quadratic in epsilon 1. Right? You contract Feynman diagonal of the polarization. Just once. So it's separately linear in epsilon 1, epsilon 2, epsilon 3. And it has the property that under epsilon I goes to epsilon I plus ki, independently for each ki, it's invariant. Okay? This is the general structure of what an S matrix is. Okay. Now, what we can do is to try to build structures which involve epsilon I dot, let's say epsilon 1 dot k2 times epsilon 2 dot epsilon 3. This is a potential structure. And so on. Moreover, the structure has to be completely invariant under S3. Permutations. Because all the 3 participating photons were identical. Okay? Actually, in the case of photons, you can easily show this problem for 3 photons there's no solution. There is no map. There is no function that is linear in all 3 epsilons, has all the properties we mentioned and is permutation invariant. okay, which of course, yeah, which would be partly an explanation for the fact that the 3-photon scattering in QED is 0.
Yeah, I mean, this is some general statement of Farade's theorem, right? I mean, any odd point photon functions are
0. Yes, that's probably true. Yeah, it's a simple property of kinematics. You know, you're just forgetting about the theory. There's just no kinematical structure that you can build that could be a potential answer. Okay? However, the same property is not true if you allow, actually the key point here that makes it 0 is the symmetry. The permutation symmetry. There are structures that are gauge invariant, but they're not permutation symmetric. Now, if you allow permutation non-symmetric structures, okay, you would have some structure, but of course, you say, well, what are we talking about there? It is permutation symmetric. However, there's context when it's not, which is in the angle stage. Now, let's suppose we don't have one photon, but r photons. And we know that the Yang-Mills 3-point function is proportional to FABC. FABC is completely antisymmetric. So the remaining structure should be completely antisymmetric, not symmetric. Okay? And such a structure exists and gives you the unique 3-point function which comes out from Yang-Mills theory. So there's a lot one can learn about scattering just by doing kinematics. Okay? That's not mainly what this lecture is going to be about. We mainly want to learn about scattering and string theory, but just to give you a rough thing. Now, what I wanted to say here was that even if you have some structures allowed, for instance for gravitons, when you do this, it turns out that the 3 structures, that general kinematics allow 3 structures.
in 4D.
Any dimension. In 4D, one of those 3 structures is parity odd. In every higher dimension, they're parity even. But it's just always true that 3 graviton scattering, kinematics restricts you to 3 possible structures. Just this little exercise I talked about, if you go home and do it for 2 hours, you'll find there are 3 structures. Okay? You have to set up the problem in a little more detail, which we'll talk about in a bit. But, okay. Now, the important point with 3-point functions is that you cannot dress these 3 structures with functions of anything. Because the things you could have dressed them with, it's like functions of pi dot pj. But those are numbers. I want to contrast this with 4-particle scattering. 4-particle scattering, let's go back to scalars, is a function of 4 momentum. P1, P2, P3, and P4. And now P1 dot P2 is non-trivial. Okay? Because that, you use momentum conservation, you can relate it to, I mean, this is sort of related to P1 plus P2, the whole thing square, by the same argument before, which is related to P3 plus P4, the whole thing square, that's momentum conservation, which is related, the wiggly means I'm not even talking minus signs and 2's, okay, which is the same as P3 dot P4. So this is related to this, but neither of them is trivial. Okay? There are 3 such combinations you can form.
ST and U.
Exactly. So P1 dot P3, P1 dot P2, P1 dot P3, and P1 dot P4, which up to some factors of 2 that we'll get straight in Polchinski's convention soon, are called S, T, and U. Now, S, T, and U are not completely independent. Because suppose I take S plus T plus U, I get P1 dot P2 plus P3 plus P4, which is minus P1 dot P1 by momentum conservation, which is minus M1 square. Some factors of 2 I'm getting wrong here. Okay? So S plus T plus U is something fixed.
For 2 independent.
Exactly. So there are 2 independent pieces of scattering data, S and T or S and U or whatever. Because their sum is something fixed by kinematics. Is this clear? Okay, excellent. So what I wanted to contrast our earlier 3-point discussion with was the 4-point discussion, where you see we have a 4-point function, even for scalar, could be an arbitrary function of, let's say, S and T. Okay, not completely arbitrary. The 4 scalars identical, because there has to be permutation invariant. That puts some constraint on the function of SNT, which we might discuss at some point. But but basically a function of SNT. There's an infinite amount of data in a function. Similarly, 4-point scattering of 4 photons, let's say. You have to list the available structures, and once you've got a structure, you can multiply it by an arbitrary function of SNT. So there's infinite amount of data in 4-point scattering. There's only finite amount of data in 3-point scattering. Okay? So 3-point scattering is infinitely simpler than 4-point scattering from the point of view of what the allowed space of answers. Specifying a 3-point scattering amplitude is specifying a vector in a finite dimensional vector space. Right from the beginning, you know that there is some finite dimensional vector space where the answer has to be. You just have to find where. The dimensionality of the vector space for bosons is 1. Dimensionality of the vector space for other more complicated particles may be larger, but it's finite dimensional always. On the other hand, scattering a 4-point function, specifying a 4-point function, is specifying functions. It's not finite data. So 3-point functions are much simpler than 4-point functions. Conversely, 4-point functions are much more interesting than 3-point functions. Okay, so this was just to set the context. Is this clear? Any questions or comments? So for instance, in the case of gravitons, I told you there were 3 possible structures. So every scattering amplitude is A1 times first structure, plus B1 times second structure, plus C1 times third structure. So the finite dimensional is a 3-dimensional vector space of A, B, and C. Okay, the space of structures. The point is that right from the beginning, kinematics tells you that the final answer is a linear combination of a finite number of structures.
3-point, you cannot have functions of that, and
because there's nothing to have a function of. Yeah. Whereas 4-point, similar analysis with structures, but then you can dress these structures with arbitrary functions of ST and U. Is this clear? Okay, good. So now that we are oriented, what we want to do is to compute the scattering amplitudes for 3 particles in string theory, and we're going to do it in various examples. See, for 3-point functions, it's an interesting question whether we could compute the most general answer. And you know, the difficulty in that would be in labeling the most general answer. Because what you would have to do is to find the most general BRST invariant operator. And we know the rules for that. And we know how to count that. Same number of such operators as light cone gauge. But the actual form of the operator is not the form from light cone gauge. So everything that we do, if you could find an efficient way of labeling those operators, you know, just writing down those operators, you can plausibly just find the 3-point functions of all states in one shot. I've never seen this done actually. Okay, we're going to work out specific examples, the examples that are most important to us. It would actually be interesting to be able to do things a little more generally. Might be worth thinking about. Maybe somebody has done it. Okay, but we're not going to try to do that. Okay, good. So the first question we're going to have to ask ourselves is, what do we want to compute? Life here is very easy. Life here is very easy because we're on a sphere. So let's say we are at the point Z1, Z2, and Z3. All 3 points, remember, are fixed. So there's no integrals left to do. So we just have to compute some numbers. Okay, this is somehow tied to the fact that 3-point functions are so simple. Okay, now every fixed vertex operator, remember, came with an insertion of C and a corresponding insertion of C bar. I'm going to write whatever there is for C, and C bar will go for the ride. And then along with that, there's O of Z1, O of Z2, O of Z3, where O was the vertex operator corresponding in the matter sector corresponding to the particle you wanted to scatter. So this is the expectation value we have to compute. Okay. Now, there are various things that, okay, let's first start computing. You see, this expectation value is a product of two expectation values. There's the BC-CFT that knows nothing about the matter part. And then the matter CFT knows nothing about the BC part. So product of expectation value of C1, C2, C3 and expectation value of O1, O2, O3. Okay? O's will depend on what states we're scattering, but the C's are universal. So let's start with by computing C of Z1, C of Z2, and there's also C bars, right? I've not written it. C of Z3. Let's start by computing that. Okay. Now, this is of course a quadratic theory, so we could just do the calculation. But there's an even easier way than doing the calculation. And it goes this way. Look, what do we know about this function? First, we know that it's a completely analytic function of Z1, Z2, Z3. We know it's completely analytic because were there no other insertions, the Schwinger-Dyson equation for C1 was that del bar of C1z was equal to 0. This can fail with insertions, but the OP tells us the singularity is at insertions. And there's no singularity when C hits C. Okay, so the OP captures the entire lack of non-analyticity when an analytic operator hits something and something else. Here there's none of it. But we know a little bit. So firstly, we know that this is completely analytic. Secondly, we know a little more. We know that this function, whatever it is, vanishes at Z1 equals Z2. Because then we get the insertion C squared, which vanishes. So we know that this analytic function, whatever it is, has to have a function of Z1 minus Z2, a function of Z2 minus Z3, and a function of Z3 minus Z1. So it's got to be this times some f of zi's, where f of zi's is analytic. Then we know, in addition, we know that this f of zi, that the whole function, because the weight of c's was minus 1, we know the whole function has weight minus 3. Okay? So this has got to be a function of weight 0 that is analytic everywhere on the plane.
Which is a constant.
Which is a constant. Okay? Now, working a little harder, we could even reconstruct the normalization of this. How would we do that? Let us remind ourselves that the let's do the following. See, C of Z1, C of Z2. Let's compute this OP a little more seriously. Okay, as Z1 goes to Z2, there's no singularity. So we get, what is the coefficient of the 0? It is simply, it's just Taylor expanding the scale. So suppose we do it near 0, C of Z times C of 0. It's simply equal to Z del C, C of 0. Well, C, sorry, yeah. Okay, so if we take the coefficient of this as Z1 goes to Z2, we simply get del C. Then we evaluate that object with another C. Okay, that gives us a C. We can proceed this way and find the coefficient. I won't try to actually do it, but this information here is actually enough if you work hard enough to find the coefficient as well. We won't need it because we'll determine the coefficients in the end by something else. But I just wanted to say that. Fine. So what we have is C1, C2, C3 is equal to some number times Z1 minus Z2, Z2 minus Z3, Z1 minus Z3. Excellent. You see, we got this with doing almost no work, which is what all of us like. Okay. Okay. Now let's move on. Now we want to move to the matter sector. So the first thing we need to know is what are the kind of vertex operators we want to compute the what are the kind of vertex operators we want to compute the expectation values of.
So you want to sketch tachyons first?
Yeah, we want to do tachyons first, but I'll just remind you in general what the structure of what we're going to do. These were operators such that C times O were BRST invariant operators. You remember the structure of that. There was one representative of BRST cohomology, or one class of representatives of BRST cohomology, which was what we called OCQ, old canonical quantization representatives. Okay? O was equal to 1, 1 primary. And such that any operator, that if there was a primary that was also a descendant. Okay, so that O plus L minus n of chi should be identified with O. The BRST closeness told us that O had to be a 1, 1 primary. And the BRST exactness, something was that two operators gave you the same, were in the same BRST cohomology class and therefore gave you same amplitudes, was true provided this was the case. You remember this, right? Now, in the case of, now these O's were made out of matter fields. All our O's were of the form e to the power I ki xi times something. Okay? Why e to the power I ki xi? Well, this is because, firstly, it's possible. It's like a primary operator by itself. But secondly, because in space-time, this is what gives the particle we are scattering momentum. We want to scatter particles with momentum. So clearly we need that. Okay? And then whenever this multiplied was chosen in a way such that the multiplied operator was a 1, 1 primary. Okay? And anything that generated that two primaries that were related like this were the same. At the level of the tachyon vertex operator. So now, this object here, the object that we multiply with, could be was a matter operator made out only of derivatives of x. Okay, and so we graded our BRST cohomology by the dimensions of these operators. The lowest elements of BRST cohomology was when the direct dimensions of these operators were 0. In terms of oscillators, these were the operators made when we had no oscillator excitations. Dual to states with no oscillator excitations. You remember operator state map? This operator, this part of the operator just made it dual to the state having momentum in the 0 mode sector. That's dealt with. Now we have to deal with the state in the oscillator sector. The oscillator sector, we had an oscillator level. So we could start with oscillator level 0, at which case we had the particle that we called the tachyon. Okay, this had to be, so suppose we had, this was 1. So we had to have this be a dimension 1, 1 operator. But the dimension of the operator was minus k mu squared by alpha prime by 4. So that was equal to 1. So this was equal to, plus. So this was 4 by alpha prime. K mu squared was equal to 4 by alpha prime. And now this k mu squared was minus mass square, because that was ki squared minus k0 squared. Minus m squared. So m squared was equal to minus 4 by alpha prime. That's why it was the tachyon. Okay, that was one possible element of BRST cohomology, one that we will deal with a lot. Okay, just because it's so simple. But there was another class that we worked out in great detail, and that was BRST cohomology at level 1. I don't know if you remember it. We started with the 28-dimensional vector space. at level 1, 26 dimensions of the 26 oscillators, and then the additional 2 coming from B minus 1 and C minus 1 on 0. Okay, and then we looked at BRST cohomology and we found 2 states were killed by the requirement of BRST closeness, and then 2 additional states were equivalent to each other by BRST exactness. Okay, and our final result there, we'll check that also from this point of view in a minute, was that we could have alpha mu minus 1 times zeta mu. Zeta was just some number times, of course, always e to the pi k dot x. Now the whole operator had to be dimension 1, 1. This guy was already dimension 1. So this operator is some dimension 0, 0 guy, which means k square is equal to 0. Okay? And now what about this guy? This guy here has the zeta mu. This zeta mu had to have the property that zeta mu k mu was equal to 0. That was needed to make it actually primary. And it had the property that zeta mu was equal to zeta mu, or was the same as zeta mu plus k mu. This was the condition that of BRST equivalence. Let's remind ourselves why this was needed for primarity. Okay, for primarity, we need that all ln's with n positive annihilate the operator. Okay, we need all ln's with n positive annihilate the operator. Let's work this out in state language. L1 has a term which is alpha 0, alpha 1. This will be the only term that's important. It's the only term that's important because we've got an alpha minus 1. Okay, so because it's 1, if you have alpha 2, alpha minus 1, the alpha 2 will kill it. Right? It has at least one annihilation operator. At least one annihilation operator because there's a 1. This annihilation operator better be a 1. Otherwise, it'll kill the state. This state it won't kill. Acting with this on this gives what? Alpha minus 1 kills the alpha 1, but replaces it with alpha 0. Alpha 0, you remember, was just proportional to k. And therefore, we get k dot epsilon is equal to 0. So the condition that L1 kill the state, namely, that's part of the requirement that it be primary, which was the condition that it was BRST closed, was the condition that k dot epsilon was 0. Is this clear? Okay. On the other hand, the condition that L minus 1 acting on anything produces a BRST equivalent state will give the condition that epsilon goes to epsilon plus epsilon and epsilon plus k are the same. How do we see that? We see this as follows. Suppose we take L minus 1 acting not on this state, but on e to the pi k dot x. I'll first work with our state language. There's actually a very cute way to say it in operator language, but first let's do it in state language. Okay. In state language, L minus 1 has a term that is alpha 0, alpha minus 1. Okay. This is the only state that acts, because if we had an alpha minus 2, then there would be an alpha plus 1, which will kill the state. It's the only state that gives you non-zero when acting on just, what is the oscillator vacuum, because you have to establish a state that has no annihilation operator. a term with no annihilation operators. There's only one such. Okay, we act on oscillator vacuum. We'll get, of course, e to the pi k dot x, but also alpha minus 1 mu, alpha 0 mu, which was k mu. But this is a state of this form. Where do we write that down? Yeah, of this form with epsilon mu being replaced by k mu. By the way, is the state BRST invariant by itself? Would you get BRST closedness? Yes, you would. Because when you act with L1, which is the only non-trivial one, you'll get 0. Because that only required that k dot epsilon was 0. Epsilon has k, so it requires that k dot k is 0. But that's true. Okay? So this is one of those null states. The states that was BRST closed by itself, but because it was BRST exact. Okay? So the net result is that on the holomorphic side, level 1 BRST cohomology in the matter sector are states of the form epsilon dot alpha minus 1 of mu, epsilon mu dot alpha minus 1 of mu, such that epsilon dot k is equal to 0 and epsilon is to be identified with epsilon plus k. Does this remind you of the discussion we had for photon scattering amplitudes? Of course it does, right? Okay, this is the string theory way of producing gauge invariant S matrices in space-time.
And this is true only for open strings, because in closed strings there's no photon anyway.
But you see, there is an analog in closed strings. Now,
when we're doing
gravitons, but let's first look at it technically. What we said here was true for the holomorphic. Wait, but before that, let me just tell you about this one cute thing. Look, there's a simpler way to compute L minus 1 in operator language. You could do all of these in operator or state language. I avoided using the operator language because we'd have to draw the contours, and this was a bit easier. But in this case, what is L minus 1? How does L minus 1 act on any operator? L minus 1 has another name. Derivative. Right? It's momentum. Okay? So L minus 1 in operator is del z on e to the power I k dot z, which is equal to del z x mu k mu. Sorry, k mu del z x mu on e to the power I k dot x, which is precisely the vertex operators of the form we looked at. Alpha minus 1 is del z in operator language. So in operator language, the operators were, in operator language, our operators were del x mu epsilon mu e to the power I k dot x, such that epsilon dot k was 0 and epsilon goes to epsilon plus k is a redundancy. And that redundancy is generated precisely by L minus 1, which was this one. So you see that anything where epsilon is replaced by k is a descendant, because L minus 1 acting on something, just because it's a derivative. Is this clear? I'm just saying the same thing in many different ways, just so that you get used to it. Okay? Wonderful. So far we've only looked at what's happening on the holomorphic side, but something identical happens on the anti-holomorphic side. Now, is it possible for us to have something that is level 1 on the holomorphic side, level 1 in oscillator number on the holomorphic side, but level 0 in the oscillator number anti-holomorphic side?
Because of this matching.
Level matching condition. Another way of saying it is that the operator has to be dimension 1, 1. So that condition fixes k squared. But it fixes k squared independently on the left-hand side, holomorphic side, and on the anti-holomorphic side. In the closed string with no compactification, k left and k right are the same. It's just e to the power k dot x. So you won't have any solution for k squared unless the level number of the remaining part of the operator was the same on left and right. right? There's a mass square condition we got from the left hand side, from the holomorphic sector. We'll get another mass square condition from the anti-holomorphic sector. Won't have any solution unless the oscillator levels of the left and right moving sectors are the same. So it's obvious. So we can have either level 0. So the first operator is both left and right, e to the pi k dot x, where alpha prime k squared by 4 alpha prime k squared by 4 is equal to 1. Okay, m squared is equal to minus 4 by alpha prime. Okay, so we have this. The second thing is we can have epsilon mu, epsilon tilde nu, zeta tilde nu, e to the pi k dot x, where k dot zeta is equal to k dot zeta tilde is equal to 0. And independently, zeta mu goes to zeta mu plus k mu. Zeta tilde nu goes to zeta tilde nu plus k mu. These are independently, have to be redundancies. Okay? So, now we've said epsilon mu, epsilon tilde nu, but scattering amplitude is going to be linear in epsilon. So really what we have is a 2 tensor, because this is a basis that builds all 2 tensors. More precisely, we could have just any 2 tensor. Zeta mu nu. Okay, zeta mu nu with the properties that k dotted with this from the left or the right is equal to 0, and zeta mu nu goes to zeta mu goes to k mu alpha nu, any alpha, plus k nu plus beta nu mu k nu, any beta, is a symmetry. Now this zeta mu can be decomposed into 3 parts. Let's do that decomposition. It could be decomposed into
Graviton,
exactly symmetric and symmetric traceless, symmetric trace, just the trace, and the antisymmetric. Okay. Now, sorry. Sorry, I said this could be anything. It has to be something that continues to obey the conditions of what zeta mu is. So it has to continue to be traceless. No, it wasn't traceless, sorry. It has to continue to be, this zeta alpha dot k has to continue to be 0. Right, and beta dot k has to continue to be 0. Okay, excellent. So the first thing we see is that because alpha dot k and beta dot k have to continue to be 0, if we take the trace, this gauge transformation doesn't act. So this trace part is just a scalar which has no gauge invariance. Okay, so the trace part of zeta is a scalar with no gauge invariance. So the trace gives some scalar which we'll call the dilaton. However, the symmetric and antisymmetric have this gauge invariance. In the symmetric and antisymmetric, alpha and beta either plus each other or minus each other, because it has to be symmetric and antisymmetric. Okay, so in the case of symmetric, this is the condition that h mu nu goes to h mu nu plus alpha mu k nu plus k mu alpha nu. And the gauge transformation for the antisymmetric is that b mu nu goes to b mu nu plus alpha mu k nu minus k mu alpha nu. Okay, both these are familiar gauge transformation properties from the point of view of space-time. From the point of view of space-time, this guy is a linearized diffeomorphism. How do you know it's a linearized diffeomorphism? Well, all of you know that under a diffeomorphism, the metric changes like Lie derivative of a vector. Delta G mu nu is equal to del mu zeta nu minus plus del nu zeta mu. Well, if we are looking at small fluctuations around flat space,
How these two vectors become same? I mean,
how they because you want the path that remains symmetric. You see, the way you should think of it is that there were two vectors here. There are also two vectors here. This is what you think. Sorry, unrelated. Okay, I'm just taking symmetric and antisymmetric linear combinations of the old alphas and betas. Okay, but now in around flat space, del mu is k nu, so that reduces to this in momentum space. Okay, so this is the gauge transformation of a linearized graviton. So the symmetric part of this, very plausibly, and we will see in great detail, is the graviton of string theory. Whereas the antisymmetric part, well, what is that? Well, look at this gauge transformation. You see, let's write it in form language. B is an antisymmetric object, so that's a two form. And this is the gauge invariance. B goes to B plus dA. Oh, d beta we called it. Where beta is a one form. Because d beta is the fancy notation for this object, perhaps with the minus sign. Okay, so this looks like a gauge transformation that generalizes Maxwell gauge transformation. Because Maxwell gauge transformation, we had A, which was a one form, and went to A plus d chi, where chi was a zero form, a scalar. Here we have a two form, which is the same rule, except that the gauge parameter now is a one form in order for the rule to make sense. Now, when we were studying Maxwell theory, we knew how to make sure that our actions were always gauge invariant. We built actions out of dA, so that it would be gauge invariant because d squared was 0. What will we do here? We do the same thing. We'll build actions out of dB, which will be gauge invariant because d squared is 0. dB here is a 3 form and it has a name. It's called h. And the simplest action we can make will be integral h mu nu alpha, h mu nu alpha. It's the analog of the Maxwell action. Notice that this is, despite being 3 index, it's also a 2 derivative action. Okay? So, what we are seeing is that string theory is sending us into a theory in which the massless degrees of freedom are a scalar. That is the trace of this tensor. Apparently a graviton, symmetric part of this tensor. And apparently a 2 form potential or 3 form field strength. Okay? These are the guys we want to get to know. We want to compute their scattering amplitudes. One of the things we will check is we will check to see whether the scattering amplitude we get agrees with, for 3 gravitons, agrees with the scattering amplitude for Einstein, 3 Einstein gravitons, at least in the low energy limit. Now I want to emphasize that it's not much of a check.
Yeah, I mean, because it is Einstein low energy limit. I mean,
how do you know?
No, I mean, any massless spin to field is at low energy uniquely, at low energies, I mean, if we are ignoring the higher order terms, that's uniquely Einstein.
Yeah, right. That's basically it. That's basically it. And in addition, at the 3-point level, just the algebraic problem of finding 3-point functions just has 3 numbers. So we're bound to land on this 3-number structure. Okay? And now, as it turns out that the 3 numbers multiply a structure that's 2 derivative, that's Einstein. A structure that's 4 derivative, that's actually generated by what's called the Gauss-Bonnet action. and a 6th derivative term, a structure that's generated by Riemann cube term. Now, if you generate these terms with derivatives, they will have to come with additional powers of alpha prime for dimensional reasons. So the low energy limit, like you said, you're just bound to land up on Einstein. Because you might, see, what can you get? Since the whole structure of string theory will very carefully preserve the gauge invariances, you're bound to land up on the structures we talked about at the beginning of the lecture. What you can get is A times 2 der. Let's work in normalization in which A has dimensionless. If there's some alpha prime for A, we take it outside overall. Plus alpha prime B times 4 der. Because it has the same dimensions. So B has to be a pure number, this has to be alpha prime pure. Plus alpha prime squared times C times 6 der. Okay? Now, in the low energy limit, this dominates over this and this because these factors of alpha prime times extra derivatives. So whatever we get at the low energy limit is bound to be the Einstein scattering. It's just not much of a check. A bit more interesting that it works. It's more interesting. You see, the theorem that you quoted, Upmanyu, is some guess. Yeah. It's saying if you have an action that comes from a local Lagrangian, that kind of thing. But you know, in string theory, there's no obvious local Lagrangian. So just the string scattering amplitude at the algebraic level could have given other structures than what you get from Einstein gravity. For instance, Einstein gravity for graviton scattering amplitudes will have poles, because you can have structures where a graviton is exchanged.
Yeah.
That will give you a pole. But you know, without knowing anything else about string theory, it's not clear that you'll get only poles. You might have got a double pole. In which case you could have got a completely different structure from Einstein gravity. The algebraic thing, and here just algebraically you were forced to get Einstein at low energies. At the 4 graviton level, algebraically that's not clear. Some deeper way it may be clear. But that's then a great check that string theory is obeying that deeper stuff. Okay? So we will come.
Could you please repeat the last statement? I mean,
yes.
You're saying that string theory is repeating what structure in Einstein gravity at higher orders?
For instance, that the only singularities that appear in S matrices are those associated with the exchange of physical particles. Okay? If that were not true, then we could have some 2 derivative kind of, some dimension counting, something that is 2 derivative dimension counting, but with higher singularities and much more complicated and interesting S matrices than that of Einstein. It's not clear that in the low energy limit in string theory at the algebraic level, the amplitude should reduce to Einstein. Meaning, let me say this more clearly. Suppose you took the following algebraic exercise. Can I write down an S matrix whose alpha prime goes to 0, which is consistent with all the gauge invariances, and whose alpha prime goes to 0 limit differs from Einstein at 4 derivative order? Answer, sure you can. Sure you can. You have to put in some more structure to get Einstein. For instance, that the only singularities come from exchange of 3-point and so on. Okay? On the other hand, at the 3-point function level, just that algebraic question had only 3 solutions. So unless by some coincidence A turned out to be 0, we were bound to, at low energies, hit Einstein. So the 3-point was not much of a check. The 4-point will be a much more interesting check that we're actually getting Einstein theory. Nonetheless, we will compute this.
And just out of curiosity, if we actually compute the usual low energy effective action function,
yes.
the usual beta function method,
yes.
do we end up with the exact same ABC coefficients?
Yes. Yes.
I mean,
yes.
So they are related in So
Exactly, everything works out as you expect from space-time intuition. So there is a Gauss-Bonnet term with exactly this coefficient, and a 3-Riemann term with exactly this coefficient. And you will also see that in the superstring, both these terms will be 0.
oh. So I mean it's
Which is related to the fact that the type 2 effective action starts with Riemann to the 4. Okay, everything works out. Everything works out. But I'm saying at this level of our study of the theory, just from the rules of string scattering amplitude, wasn't so clear things should work out. So it's really, it's really a check that everything is falling into place, and it's amazing how it works. Okay? Okay, fine. So this is like the lay of the land. Now we understand the operators we want to scatter. We have computed the C 3-point functions. Now what we have to do, what remains, is to compute the matter 3-point functions. And then we're in business. Fine, so let's start doing that. Okay. Okay. What we need, so let's start working with tachyons. Okay, actually maybe we should just do it once and for all. So what we need is to know how to compute the expectation values of e to the power I k dot x and perhaps z of del mu of z1 and perhaps del of z. Let's first do the simplest case. E to the power k1 k2 dot x of z2 e to the power I k3 dot x of z3. Okay. Now we already know the answer to this question, right? I'm just going to write down the answer. We've computed this using Wick's theory. Do you remember? Okay, I'm just going to write down the answer. We will come back in the, there's one subtlety though. All our previous computations were on the plane. We should really be working on the sphere. Okay? There is one question about whether that makes any difference or not. The answer is no. Okay? The real issue has to do with the zero mode on the sphere, which in the end, all it does is impose momentum conservation. But just so that we don't get stuck in formalism, I'm going to write down the answer that we, on the plane, we take for granted it also works on the sphere, because the plane and the sphere are the same except for that one compactification point. So it's plausible. It's something we have to think about, but we'll do the thinking after we get the answers. Okay, let's postpone that for a minute. Polchinski has a long discussion on this. And it's correct, you should have a long discussion on it, but in the end you get it right. It's a bit disappointing when you get the answer you would have written down anyway. Okay, okay, so let's remember how that goes. Okay, this is expectation value is exponential of sum over, in general, if you have many of these, you have the sum over every pair, I less than j, let's say, meaning k1, k2, k3. I just want it pairwise, and each pair will come with a ki dot kj, will come with a minus sign because I square, and will come with a 2-point function, which is alpha minus, so the minus goes, alpha prime by 2 log of z1 minus z. Okay. Now, yeah, let's just work with this and we come back for the longer discussion. We don't contract points here with themselves because this was normal ordered. We're not allowed to do that kind of contraction. Okay, so it's just this, right? Excellent. Let's just work with this and proceed. So this guy is very simple. This guy is what? It is Zij to the power ki dot kj alpha prime by 2. So let's immediately work out now 3 scattering amplitude. Okay, so what is there to work out for 3 tachyon scattering amplitude? Well, we've got 3 tachyons at Z1, Z2, Z3. Each of them gives us this factor. And then we had a factor of Z12, Z13, Z23 from the C ghosts. And that's it. Now, this looks complicated, but remember our discussion with 3 particles, ki dot kj is fake. So let's work that out now more seriously with numbers. Let's do k1 dot k2 half of k3 squared minus k1 squared minus k2 squared.
This is just minus k2, minus k squared.
Okay, which is equal to minus k1 squared by 2, for instance, because they're all the same.
Which is positive.
Which is equal to, now
No,
k
is minus m squared.
K was, exactly. So K was, K squared was equal to 4 by alpha prime.
Yeah, sorry.
Right? So this is equal to 2 by alpha prime with a minus 1. But now we want alpha prime by 2 of this. So what do we get? We get Zij to the power minus 1. We have 3 of these factors. Exactly cancel these 3 guys. So what's the answer? It's 1. Now, already something nice has happened. What is the nice thing that's happened? The nice thing that's happened is that the answer did not depend on Z1, Z2, Z3. We knew on general grounds that the answer cannot depend on where we fix our fixed vertex operators. If the answer depended on Z1, Z2, Z3, it would have been meaningless. So it's very beautiful the way it cancels. Okay?
It could have been said in the first place.
What? Could have been said in the first place, but you see, at our stage of the study of the theory, we want to check that it's working.
Yeah.
Right. And now as
Now for higher point functions also the same statement, that statement that it is independent of the position. So
Yes. Yes. It will always be true. Sometimes we will check it, sometimes we will just use it. Okay. Once we get but at least the first few rounds we'll check. Just so that we start getting used to it. All good? So 3 scattering amplitude, it's pretty boring. It was 1. What else could it have been? It was a number. Okay.
Just out of curiosity, if we were actually working in a sort of on a tachyonic background, I mean, I don't know whether that's the right terminology, but I was wondering how we could actually do some Feynman diagrammatics around some maxima of a potential, because we
See, every time you try to do loops around this, you'll run into trouble. If you do just tree exchange, you can do it, right? What you'll get is exchange of wrong sign pole. But okay, will be an exchange of a wrong sign pole. When you try to do loops, you will have loop diagrams involving the wrong sign mass. That will lead to infrared divergence. It's because when you're doing loops, what you're doing is a Gaussian integral. And you'll do a Gaussian integral of the form e to the power ax squared rather than e to the power minus ax squared somehow, which will lead you to trouble. But at tree diagrams, don't see any problems. Another way of saying it is that tree diagrams are classical.
Yeah.
There's no problem in classical physics with starting or fine-tuning to the top of a potential. Quantum mechanics, that's not allowed. Why is it not allowed? What's the difference? Suppose you had a particle on top of a hill. I placed it. It's a question I sometimes ask in entrance exam, in TIFR entrance test. I have a particle here. I put it on top there. This is a wire. And classically I can do it. It will stay forever. Is there a maximum time it can stay quantum mechanically? But? Uncertainty, exactly. You see, this thing has a wave function. If the wave function is broad, it means there's some large amplitude for it to be here, which means it will fall. If the wave function is very peaked, initially there's no amplitude, but the wave function will spread very fast. So you can find the optimum wave function and then check with that optimum wave function how long it takes to fall. Of course, it's time that goes to infinity as h bar goes to 0, but in an interesting way. Okay. It doesn't matter. So I'm saying that this phenomenon, as soon as it becomes quantum, you can't put something at the top of a hill.
I mean, it will be some instanton like problem. It will be
not instanton. It's much simpler because it's unstable.
No, I mean the time scale. I mean that will be exponential, exponential in -1 over h bar or something.
The time scale. My memory is that it's a log of h bar, but it could be that I'm remembering. Maybe you're right.
No, because in instanton.
But this is not an instanton.
Okay, yeah. Maybe.
Yeah, an instanton requires tunneling through a potential. This does not have to tunnel, just has to roll.
Yeah. This is real time.
Yeah, it's just shoop. Yes, it should be much faster then. I think it's log h, but it's pretty fast. Or 1 over log h, but whatever. There's some log involved. Okay. Fine, you guys can work this out. We won't do it in class. Okay. Excellent. So there's no issue with doing the end results. There's no issue with working classically with a tachyon. Though it's an uncomfortable thing to do. You're doing something strange. But at the technical level, you won't run into trouble. Unless you start doing loops, at which point you will get uncurable infrared divergences, which will reflect the fact that you start doing anything here and you'll be forced to fall in. You will get that. Okay? That's why we will never do loops, never seriously do loops for the bosonic string. But we will do it for the superstring. Okay, but tree diagrams, no problem.
So, bosonic string, I mean, is in general the genus expansion with tachyons, I mean, is that badly behaved?
It's ill-defined. You try to do the integral, you'll get infinite. Okay, now there is sometimes a way of regulating away that infinity, but it's completely artificial. As you say, it's like working it's trying to do loops in around the parametric magnetic phase of a substance that is actually a ferromagnet. It's totally ill-defined. You'll get terrible infrared divergences you can't cure. It's just telling you you're working around the wrong vacuum. You fix your vacuum before you can get sensible results. So a bosonic string loop, to get a number from loops in the bosonic string is a fool's game. It's completely well defined for the superstring.
But this problem wouldn't afflict us if we are considering vertex operators let's say purely gravitons or...
It would afflict us with any vertex operator because in a loop everything is created.
Yeah, that's what I was thinking.
That's the great thing about this tree stuff. Okay, we're going to get into deep trouble anytime we compute any loops of anything in the bosonic string. You can formally analyze loops of the bosonic string, look at the structure and so on, but if you want to get the number and do the integral, you'll be in trouble.
Yeah, because Polchinski has a chapter on one loop amplitude.
Has the chapter on one loop amplitudes, yes. Yes, and one of the things he will find, for instance, if you try to find a partition function, you try to compute anything, he'll isolate out the tachyon part and throw it away. But if you try to compute the finite temperature partition function, something with the tachyon, you get infinity.
I mean, the Torus partition function, so for that he throws away
the tachyon piece. If you make space-time, but it's important to be computing a physical observable. Let's make space-time, put space-time on a circle.
Yeah, then
you get infinity.
Fine.
Huh? No, you'll get infinity because you'll be computing trace e to the power minus beta h.
Yeah, I mean, with the short distance, I mean, this is.
It's just that the computing it in a free theory with an unbounded Hamiltonian.
No, I'm just trying to reconcile your statement that we get infrared divergence versus when we are actually compactifying space-time.
No, we get infrared divergences. You see, all we are doing is compactifying time. We still have space.
Yes.
Now, these infrared divergences actually will be even worse. You will have to compactify to critical size to not have this tachyonic problem. Because you'll have to have the momentum here overwhelm the tachyonic mass. But then there's also always the zero mode, there are always the winding modes. Basically, you'll never be able to make sense of it. Never be able to make sense. Yeah. Right. Infrared divergences maybe was badly said. What you will get is divergence for all momenta such that ki squared is not larger than mod of m squared. Because you see, what you're trying to do is a path integral like this, d phi exponential of phi of p, phi of minus p, p squared minus m squared. This path integral makes no sense unless p squared is larger than m squared. Sorry, so Upmanyu, I was saying that, I said this a bit badly. One should not say infrared divergence. More precisely, you will have divergences associated with every momentum such that mod spatial p is less than m. Because, see, this is the path integral you're computing. Exponential of minus phi of p, phi of minus p, mod p squared, which is positive definite, but minus m squared because it's tachyonic. And the integral of a phi of p for every p such that mod p is less than m is divergent. So, it's worse than infrared in the sense that not strictly zero momentum. All momenta smaller than a certain amount. It's just a terrible theory. One shouldn't think about it. Loops with it are going to be terrible. Okay. This is the whole point of inventing the superstring. We'll be able to get good answers. Okay. But all this for the future. Let's first compute 3-point functions. Okay. Excellent. Let's keep going. Fine. Now we're done with tachyons. Now I want to get a slightly more complicated 3-point function. Okay. The 3-point function I'm after is del x mu zeta mu e to the power of z1 I k1 dot x of z1 e to the power I k2 dot x of z2 e to the power I k3 dot x of z3. This is the amplitude I want. This will be associated with tachyon photon. Or if you take 2 copies of this, tachyon, for instance, graviton. Okay? Now, at the next stage, we'll put zetas in all of them. Okay. How do we compute such a thing? Well, once again, all we have to do is to use basically Wick's theorem. Okay? We have to do all the contractions available to us. Okay? So that's basically the thing we have to do, but let's see how we do this, practically speaking. Okay. Okay. So, in order to do this practically speaking, what do we want to do? We want to do all contractions So the contractions between this, this and this, we've already taken into account. Okay? What remains is contractions between this guy and this guy, and contractions between this guy and this guy. Okay? This is only one fellow. So it either contracts with something here, or it contracts with something here. It's not like you can take one of it and contract with this guy and another with that guy. Is this clear? So that's relatively simple. Okay? So let's work out the weak contractions with this guy and this guy. So all we're doing is taking some normal ordered expression and re-expressing it in terms of something times normal order. And once that something is normal ordered, only one in that normal ordered expression can contribute. That's the usual big theorem given. Okay. So what we want is, so we've got del x mu of z1, and then we're going to do all the contractions we can with e to the power I k2 x of z2. Okay, so we can use the fancy formula involving Green's function, or I find it easier not to make mistakes by just expanding. Okay, so let's do that. So what we've got is normal order this times normal order that. Okay, and then we've got del x mu of z1, and this is normal ordered sum over n I k2 to the power n x of z2 to the power n by n factorial. And then what we are supposed to do is to do every contraction we can and replace the rest by normal order. But now we can only do one contraction because there's only one guy here. So remember, x with x was minus alpha prime by 2 times log. If we're going to contract with this, we have n choices. That kills the n factorial, makes it n minus 1 factorial. Okay, so you see we're going to get an I k2. Now, because there's a mu index here, there will be a mu index here. That will be one factor of I k2 left over. Yeah, of course. Okay, n has gone away.
But there is no eta mu nu.
There is no eta mu nu. What? Sorry? You're asking whether the indices are raised or lowered? Is that the question? Let's see. So x mu will only contract with x mu here, and so whatever you get will be k mu here. That's all that's going on here. Okay. Yeah. This would have to be raised. This was raised. Right. So, okay. Maybe. Yeah, it would have to be raised. Maybe. Okay. Fine. Then the n factorial is.
making it k mu.
That's right. Yeah. And then this will be e to the power I k2 dot x2, x of z2. And there will be the minus alpha prime by 2, and then this had a derivative. So 1 over z1 minus z2. Is this clear? Okay. Now, this will multiply all the terms that we get from the other contractions. Okay. And then what remains will be normal ordered. Okay. And so what we're going to get in the end is zij to the power alpha prime ki dot kj by 2 product all three. And of course, there will be a term where this guy contracts with 3. Okay, so I should write, let me put that again. So I'll write this better now. Let me write the answer more systematically. Minus alpha prime by 2 into, I'll put an, okay, let's put I k 2 mu by Z1 minus Z2 plus ik3 mu over Z1 minus Z2, Z3 times product Zij to the power alpha prime ki dot kj by 2.
When this operator is contracting in the e to the power I k2 x2
Yes.
x2,
Yes.
in the same time e to the power I k1 x z1 can contract with the same.
It can because what you produce is another factor of normal order e to the power ik dot x. See, think of it step by step. What you do is to take product of these two operators
And the operator is left over
and then that can contract. You have to so imagine doing it step by step. Do this with this. What's left behind is this, which was e to the power k2 dot x z2 normal order times this. So think of it like this. We've taken normal order of this times this and rewritten it as normal order of, okay, first term is just normal order of del x mu times that, and second term is normal order of just this times this number. Now in the remaining contractions, the first term will play no role, because once you have normal order and you have del x mu inside, you'll get 0. You need just identity, right? Only normal ordered expression that has non-zero expectation value is identity. So I said this very unsystematically. Shall I say it properly? Let me say it once, just to make sure everyone's understanding. I'll do it step by step. I'll have to do it separately. Not quite. Let me do it separately, step by step. Yeah. Okay. Let me do it. Let me do it completely systematically. Suppose we have del x of z1. It's pi k x of z1.
That is 1.
This is 1. Then there's e to the power k2 x of z2. I k3 x of z3. Now first we'll use the theorem with this guy and this guy. So this we've just shown is equal to normal order of del x of z1 e to the power k1. Okay. Yeah. If we do it, really what we'd have to do is to have either this contracting these guys or this contracting these guys. There will be two terms. So we will have this normal ordered of this ik x of z1 plus k2 x of z2. And at this stage, times this factor, z12 to the power alpha prime k1 dot k2 by 2. That would be one term. This is when all the contractions happened here. Okay? But then there will be plus the other term, which is just normal order of these two guys. E to the power k1 x of z1, ik2 x of z2 times this times this.
And why this factor is coming?
Why this factor is coming? It's because first we do normal order of this guy with this guy.
Yes.
So this guy, this normal order goes in, and then we have to normal order this guy with this guy.
Okay.
What? But here?
No.
Doesn't matter.
Under normal order, you have to do the direct ones.
Exactly. Okay, so all we're doing is Wick's theorem. We're writing everything in terms of normal order expressions plus contractions. The thing is that every term in this will have normal order of e to the power I k. In the end, we'll have e to the power I kx1 times kx2 times k1 x1 plus k2 x2 plus k3 x3. That will be then every term. Then some terms will also have normal order of del x's. In the end, when a term has normal order of del x's, you throw it away. Right at the end, because expectation value of normal order of any expression involving del x is 0. Okay? At the next stage, what we would do here is this will fuse with this. That will give us the other z's. But also this will fuse with that. Okay? And that will give us the term with the del x's hitting K3. That will give you the second term. Okay, so you'll have two terms. All terms will have the same structure of this Zij to the power. Okay? Polchinski works this out using this fancy formula. I don't know if you remember, but we yeah, exactly, del f. And you can do it that way. And you'll get it more systematically. Okay? But I think it's more instructive to look at it, piece by piece. Okay? Go on.
First term is basically the derivative of e to the thing.
First term, not quite, because zeta and k are not the same. And it's very important, because the case where it's a derivative is the case where the state is BRST null. So that case will be trivial. So we cannot use that to calculate what you want. Okay, that's a very important point. Right? You remember, in fact, we argued that the case where it was a derivative will not be interesting because it's a descendant. Okay, excellent. Fine. Now, so we've understood what happens when we've got one vertex operator with one vertex.
You wanted to take the derivative on the only 3 to the power ikx and to get this form?
No. He was saying that, look, this vertex operator. Yeah, exactly. He wanted to take the Z1 derivative.
Xi is not equal to q1.
Xi is not equal to k. Had they been equal to k, it would have been equal. Now you might think, well, even if they're not equal, can't we use that somehow? The point is we can't, because that's precisely the case where everything will turn out to be trivial. Okay? So that's a bad way to, not a useful way to think. It's like saying that in the case that the answer was 0, we have a very easy way of calculating it. Okay. Okay, great. Now, what about if we have two or maybe 3 photons? So we had a zeta 1, zeta 2, zeta 3. You see that we're going to have, the main difference is that we're going to have an even further terms. Because in addition to the terms that we have here, we're going to have all these terms. Each zeta will multiply such a factor. Right, because these guys can contract with this and these guys can contract with this, that will give rise to the factor. But in addition, what we will have is contractions between del x's and del x's themselves. Okay.
This answer is actually zeta dot k2 plus zeta dot k.
What?
Yeah. This answer is actually zeta dot k.
Zeta dot. Zeta mu. Okay? So, one way of saying that is the following. Every insertion of zeta dot del leads to a factor of this term plus a formal oscillator, a del x tilde, which can now only contract with other del x tildes according to the usual contraction rules. Del x tilde with del x tilde prime gives us alpha minus alpha prime by 2 and then 2 derivatives of the log. Okay? So I'm going to summarize our rule that way. Our rule is every zeta mu del x mu e to the power I k dot x, the effect of this zeta mu del x mu is this. We get zeta mu times sum over I k. So suppose this was zeta I. This is k sum over j not equal to I. K j mu. All the other k's in the problem. Okay? And this will work beyond 3 points. K not equal to z zij minus alpha prime by 2. I hope I got the signs right. We'll check with Polchinski in a bit. Okay? Plus del x tilde mu, where del x tilde mu is just some formal object such that del x tildes can only contract with themselves. Okay? So every insertion of this will lead to this, and then we will also have, so we'll have a product of such things for each insertion. Then we will have a factor of zij to the power alpha prime ki dot kj by 2, product over all those. And in the end, we do the formal contractions of the formal oscillators, del x tilde. Those formal contractions give us some additional numbers, and that's the end of the problem. Is this clear? In the case that there was only one zeta, there are no formal contractions of del x tildes to do. So that gives 0. But in the case that there are many del x tildes, there will be some formal contractions left. Is this clear? Is this rule clear?
Why does del x tilde only contract with themselves?
Because that's the only weak contraction we've left out. Everything we've taken into account here includes all weak contractions of del x's with e to the pi k's. That's what all this is. But we've not taken into account the weak contractions of del x's with themselves. So that's all I'm saying. That these x tildes are allowed to contract with other x tildes.
What is the index for this del x tilde? This is
Always contracted with zeta. Oh, you're asking what is this I? It's just that this is the ith. This x tilde is at zi.
This will have zeta I, right?
Yeah, it's here.
Del x tilde will also have zeta.
Yeah, it's multiplying that.
I'm saying this zeta dot zeta will be.
I didn't understand. No, this one zeta.
And what is the oscillator amplitude?
Del x tilde has to be contracted with the rule x tilde of zi, x tilde mu of zj is equal to minus alpha prime by 2 delta mu nu log of zi minus zj. What? Yeah, x tilde only contracts with itself. You see, now in this new expression there are no exponentials left. There are only functions of z. Is this clear? So in particular, del x tilde, let's take two derivatives. First we'll get a 1 over zij, and then will become a 1 over zij square, 2 minus signs. Okay? So we will get del is equal to zij square. Right? 1 minus sign because it's a derivative of 1 over z, 1 minus sign because one of the derivatives is on the other one. Okay, so just think of this as a formal object to be contracted with this rule. And that gives you the answer. I just don't want to do it write it explicitly because then it depends on how many you contract. You know, different rule for different numbers of terms. This way it's sort of nice. Okay, now let me just check with Polchinski that all our factors of minus signs and so on are okay. V mu is minus 2I by, oh god, oh, is this open string? Disk. Let's go back to, alpha prime k just minus I alpha prime by 2 ki. Is that what we had? Minus I alpha prime by 2 ki. Lovely. And Q gives perfect. Eta minus perfect. Polchinski agrees exactly with us. Okay. Okay. All good? Okay.
These are giving the zeta dot zeta terms.
Zeta dot zeta terms, yes. Okay, so now let's do some more serious calculations. Okay. The first thing we'll do is scattering of a tachyon. Let's say the scattering of two tachyons. Let's do the scattering of two tachyons of something with a zeta tilde. Now, before doing the calculation, what should one expect? The zeta tilde, the symmetric part at least, is the graviton. What should you expect when you scatter, what term in the Lagrangian would you expect leads to scattering of one graviton of two tachyons? Like that. Well, if things are working out as we should expect, there's a Lagrangian in space-time. What's the action for the graviton? The square root g. There's del mu phi, let's call it t, del mu t minus m squared t squared plus higher order stuff. Now, there are two factors of g in this. There's in square root g, and there's g when you, in raising these metrics, let's write it explicitly, del nu g mu nu. Each of these factors will lead to scattering of two tachyons with the graviton. The coupling will be essentially to the stress tensor, right? And the stress tensor has some form. There will be a term which is t del mu t del nu t, and another term which is plus maybe relative minus half. So let's call if we call this 1, then there will be a minus half g mu nu, and then the Lagrangian L. Okay, and then in each of these, so this is delta mu nu because we're doing about flat space, and this has an h mu nu. Eta mu nu, g mu nu is eta mu. Okay, so if H is a traceless graviton, we should expect it to contribute, scatter with this guy. Okay, and we should expect a Feynman diagram that is essentially tachyon, tachyon, graviton coming basically from this vertex. Okay, so what should the answer be? The answer should be proportional to zeta mu nu, which is the graviton polarization. So suppose we have tachyon, the tachyons of particles 1 and 2, and the graviton is particle 3, k1 mu, k2 mu. That's what we should expect. Now, let us note that this k1 and k2 are essentially the same in contraction with zeta, because zeta dot k3 is 0, and therefore by momentum conservation zeta dot k1 is same as minus of zeta dot k2. So we can write that in a slightly more symmetrical way. We can write this as k1 minus k2, which will emphasize the symmetry of zeta. Okay. And basically this is the scattering amplitude we should expect to see for two tachyons going to a graviton. Actually, although I've motivated from the form of a Lagrangian, this is one of these cases where if you try to write down what could the scattering amplitude possibly have been, by linearity in zeta, gauge invariance, there would have been no other option. Actually, in this case it's so simple, let's do it. So the answer has to be invariant with zeta mu nu, a linear in zeta mu nu. Now, zeta mu nu has two indices. It is traceless. The two indices cannot contract with each other. So they must both contract with a k. We've just argued this is a unique way that they can contract with a k. So there's no other structure we can construct. There is no other structure we can construct using this structure. Now it had better be that it's automatically gauge invariant. Otherwise there's no term we could construct. Okay. Now what is the gauge invariance? Okay. It is shifting any of the indices of zeta with a k. Now k is k3, which is k1 plus k2. Now k1 plus k2 will dot k1 minus k2 to give k1 squared minus k2 squared, which happily is 0, because k1 squared is 0 and k2 squared is 0. Because we didn't. Because k1 squared and k2 squared are equal to each other. Okay, so it is nice and gauge invariant, and it's the only thing that you could have built. It's also what will come out of Lagrangian, because the Lagrangian is general coordinate invariant. Therefore, will give rise to a gauge invariant amplitude. So Lagrangian is often the easiest way to think of it physically, but in this case it wasn't very impressive. It just came from symmetries. So if there's a non-zero scattering amplitude, it has to be proportional to this. What else could it be? For the traceless symmetric part. You could have more interesting, you could have more general structures for the trace parts. Well, the dilaton coupling will in general, dilaton will also in general couple to this part. It's a little more complicated. Okay, but for that massless, the traceless part, this is all you could have. Let's check it. Okay, great. So now it's important to keep in mind that we have both left and right movers. Okay, so what do we have? First let's do this part. First we have Z12, Z23, Z13, and I'll write everything. Okay. Z12 bar, Z13 bar, Z23 bar, C and C bar. Now let's get these guys out of the way. 1 and 2 are the tachyons, and 3 is the graviton. That's our convention. Okay, so what about Z12? Z12 will be K1 dot K2. okay, that will be proportional to k3 square. This is, no, be careful, I'll be careful. That's alpha prime by 2 k1 dot k2, which is alpha prime by 2 into k3 squared minus k1 squared minus k2 squared by 4. Right? Now, this was 0, but each of these was 4 by alpha prime. Right? And was there a minus sign here? Was this accurate or did it have a minus? Minus sign? Thank you. Which is minus alpha prime by 4 into minus 2 into 4 by alpha prime. Right? So that is equal to 2. Okay. So we get Z12 to the power 2 a bit of a strange number, just a minute. Just remind, did this have a minus sign or not? In the case of the tachyons, we should have got without a minus, right? No minus, isn't it right? Yeah, no minus. Because there was an I, there were two I's, and there was minus alpha prime. No minus. Yeah, that makes more sense. So that's 1 over Z12 square. Okay, then what about Z13? So Z13, in Z13, one of these is 0. In Z13, one of them is 0 and the other two cancel each other. So you get 0. So all you get from this thing is 1 over Z12 square. Okay? So now what's left over here is Z13, Z23 over Z12. And similarly with the bars. This is left over from the C ghosts and this part. Is this clear? Okay. What is left over from here? This part is 0 because that's only one oscillator. What's left over is just this. So we get zeta mu, zeta tilde nu. Now there are two factors of I and two factors of minus, total factor of minus. So there's an overall minus. There's alpha prime squared by 4.
Z12 square becomes, oh, one of them cancels.
One of them cancels. Right? There's alpha prime squared by 4. And there is, now, this was on factor number 3. So it's k1 mu by k1 mu by Z31 plus k2 mu by Z21. What am I saying? 3, 2. And a similar factor, anti-holomorphic. K1 mu by Z bar 31 plus K2 2 mu by z bar 3 2. Now let's take each of these. Somebody has this written down, right? So I can ask you for it. I'm rubbing it out. Now let's simplify each of these. So what do we get here? So we have k1 mu by z31 plus k2 mu by z32 is equal to z32 k1 mu plus z31 k2 mu over z31 z32. Okay, z31 z32 are going to cancel this. So what we have left is 1 by z12 mod square to the minus alpha prime by 4 zeta mu zeta tilde nu dotted with z32 k1 mu plus z31 k2 mu and z bar 31 32 k1 nu plus z bar 32 k2 nu. What? 31, thank you. Perfect. Okay. Now it looks sort of complicated. And the thing that makes it look complicated is that here we have a k1 and here we have a k2. So how can we combine these z's together?
K1 is equal to minus K.
Exactly. But k's are contracted with zetas. And zeta dot k3 is equal to 0. So in contraction with zetas, each of these can be replaced by k1 minus k2. So let's replace this by k1 minus k2 by 2 and this by k2 minus k1 by 2. Okay, so the same thing is minus alpha prime by 16 1 by z12 mod square zeta mu zeta tilde nu.
That will cancel.
Exactly, exactly, exactly. That will cancel. But let's see it. And so this is k1 minus k2 mu, k1 minus k2 nu. And now what's this? This was z32 minus z31 mod square. But z32 minus z31 is z12. Okay, which therefore cancels. What?
This K1 minus K2 and K2 minus K.
You're saying there's an extra minus sign. No. I've taken that account in making this z32 minus z. Anyway, actually part of the reason I did both together was that if I made a sign mistake here, I'll make the same sign mistake here. So it won't matter. Okay. And now you see what the answer is. It's exactly what we expected. The key point was that the z's cancelled. After that, what else could we have got? But we get something, right? I mean, we get this thing. And so it is exactly what we expected, also with a number. It's sort of an interesting number. Okay? All this we're going to try to make sense of, the number and so on, we're going to try to make sense of. Right now we'll just try to do a few experiments and then we'll come back and try to make sense of everything. Okay, excellent. Do we have time for one or two more computations? Okay, let me be nasty and leave this for you as an exercise. Can you compute the 3-point scattering of 3 gravitons for me? okay, using the same technique. Many more terms, do it at Z1, Z2 and Z3. Show me that the Z dependencies cancel. Okay, and get me the final answer. Is this okay? We'll reconvene on Friday to take this out. Yes, why? I'm out from Saturday onwards.